Hi, I'm Andrew.
And I'm Tyler,
Welcome to our Power
engineering
Final.
project. Before we continue, I want to talk about the load profile of Cal Maritime. Here we have the kilowatt hours for the year of 2020, January through December. And this was not a typical year because students were leaving at sporadic times, as well as the ship stayed on campus when it usually leaves. So uh, this bottom is kind of typical, is a little bit higher than typical. The ship was on campus, but this is kind of what we see every year when there's no students on campus. Our load is the lowest. This middle region is when there are some students back for phase 3 face-to-face and dockside steaming. So the load was higher because we had people living on campus and there was activity. This upper region is where we would most likely see normal operating during typical years. And this is when all the students are back on campus. We have the ship on campus, and it kind of ranges depending on the season. Summer months being a lot more load because of the AC being used, and then winter months being lower. And then just keep this in mind because we will be coming back to this in future slides. All right, so our energy cost per month, we have peak costs and off-peak costs being the highest, and our total cost per year is around $480,000 or $55 per kilowatt hour, and we'll drastically reduce this. So our demand cost comes out to about $134,000 per year and brings our total electrical cost to about $600,000 per year for campus.
All right, so our initial plan to cut these costs was to implement a combi system of solar panels and flywheels. And so flywheels work by taking a 5,000-pound steel disc, spinning it up to about 50,000 RPMs on its motor generator shaft, which is sealed in a vacuum cylinder with hybrid electromagnet bearings to reduce friction. And so you spin it up to maximum RPM by taking some power from the grid. And if they lose power as they slow down, the kinetic energy is converted back to electricity via the motor generator in the shaft. And solar panels utilize the light from the sun to allow these photons to knock electrons free from atoms, which generates a flow of electricity.
All right, so looking at some applications for this technology, flywheels have two main applications. Their biggest application is frequency stabilization for large power plants, and we'll get into why after in the next slide. They're also really good at, not as well, but they have short periods of load offset. Again, talk about this in the next slide. Solar is really efficient during about 9 a.m. to about 4 p.m. And in our situation, because PG&E changed the tariff rates, if you combine these two systems to where you use the solar energy to ramp up flywheel and store the energy and then offload that energy during peak times, you can optimize your energy savings.
And so here's some numbers in terms of flywheel power generation. And so each flywheel is good for about 30 kilowatt hours per cycle. There's some idling losses though, which really just means it's going to cost 3 kilowatts per hour to keep them spinning at their rated RPM, which is typically 50,000. And they're designed in two different ways. They can, well, in terms of power output, they can be set up so as to deliver 190 kilowatts per 30 seconds or 50 kilowatts per 35 minutes based on how drastically the power is needed. And they typically operate three-phase 480 volts AC, which is very standard. And they're generally, the flywheels we examined, 7 feet by 3 feet, but that's not really a big issue since they're typically buried underground for safety purposes.
All right, so solar technology, really to generate the most amount of power with solar, you need a lot of square footage. And the best place to put solar is rooftops, and Cal Maritime has a ton of these. We'll go over some examples of where we could put it on campus, but something to keep in mind is that putting them on top of roofs means that you'll be able to tie into the school's electrical distribution network really easily. And this picture on the left shows an example if you put a 260 kilowatt system on top of upper residence. See, we can save about $50,000 annually. And imagine if we put them on more buildings.
So here's the electrical diagram of Cal Maritime, and the main tie-in is a 12 kilovolt main switchgear, which is relatively close to Egypt. And you can also see in the diagram where these lines go to, which are conveniently located by pretty much every rooftop that we plan to implement solar to. And so as for the flywheels, we would plan to bury them in this dirt lot where the auto shop used to be up by Egypt, which is a very convenient location, seeing as how there's currently nothing there and it's relatively isolated from main campus foot traffic. So if there was some kind of failure with the flywheels, not only are they buried underground, but are not really in the vicinity of immediately injuring anybody. And here we have pictures of all the locations that we would plan to implement solar, which all of which are ideal because the sun is not impeded by any obstacles. And so in the top left, we've got the Northern Residence Hall, also known as the hotel. In the top middle, we've got Egypt, which, as I think has been said already, we were planning to put solar carports. In the top right, we've got all the classroom buildings, the dining center, and lab buildings. In the bottom left, we've got the upper residence hall, which my colleague already went into a little bit of detail about the possible savings. And then in the bottom right, we've got the PIAC, all of which are great locations for solar.
All right, so looking at a system, a 1.6 megawatt system on campus, distributed across a few of the roofs, we can see that we get a really dramatic load offset. As you can see, we are generating the most power between 9 a.m. and 4 p.m. And actually, at 9 a.m., we're going to be making power, and which could be sold back to PG&E. And then this slowly goes back to our normal load when the campus gets up and running. But as you can see, there's a ton of room for energy savings here, which comes out to about $150,000 per year. Again, because PG&E changed their tariff times, our peak cost is still pretty high. It's decreased a little bit, but since it starts at 4 and goes till 9 p.m., we're kind of just missing the window for solar generation to pay for some of that. Our off-peak time is when we're going to save the most money, and drops our kilowatt hour cost to about $37. So savings of $17. Our solar demand drops a little bit too. I don't know if you remember, but it's about 138, so it drops about $10,000. Not huge, but something. And this is just a graph showing where you'd be saving the most money. So total energy costs is dramatically down, and you'd be saving a ton in the off-peak time and partial peak time. A little bit in the peak times, but not as much.
And so here's a graphical representation of the time it would take to pay off the solar. And this is taking into account a 1.6 megawatt solar system. And so based on the rate per kilowatt, it would affect how long it takes to pay off. So if we were getting a really good rate of like $1 per kilowatt, it would take about 10 years to pay itself off, which linearly progresses up to if we were to get $3 per kilowatt, which would take roughly 31 years to pay itself off. And so as for the carport structure in Egypt that we proposed, there's two options here. And so we roughly estimated the area to be about 70,500 square feet worth of carport structure. And so one option would be to construct these carports ourselves and then use the same solar panels we were planning on implementing with the rest of campus. And if we were to take that route, the cost can range anywhere from $700,000 to $2.12 million based on if we were to use the cheapest aluminum, which is the lowest cost material, all the way up to the highest cost material, which is steel. And there's numerous other materials in there, but figured it'd be best to give the range. And so this would increase the amount of time to pay off the solar anywhere from 5 to 14 additional years. And then another option would be to get a unified carport and solar combination through a company called Power Solar Phoenix. And for us, anything that's above 69,000 square feet and 1,000 kilowatts, which in our case, it'd be 960 kilowatts. So it'd probably be a little bit cheaper, but that would be about $1.3 million.
All right, so one thing to note, when we first started this project, we were looking at a combi system of flywheels and solar. However, looking into the cost of flywheels and the potential load offset generated by them, we decided it would not be feasible. And this was because flywheels really only have a life expectancy of around 25 years, and they really can only generate around 50 kilowatts per 30 minutes. So the amount of savings you would get would not justify the massive investment because it just would not be around for long enough to pay itself off. Something better would be a combi system with solar and battery backup and storage.
And so solar aside and flywheels aside, we looked into a energy savings plan through Siemens Smart Building Technologies. And so Siemens has a pretty wide range of specialization, all the way from automation, tariff optimization, equipment monitoring, carbon footprint reduction. So we looked into some of the possible implementations of this smart building system. And some of these examples consist of Marriott hotels, which saved $1 million per year by implementing chill water variable frequency drives and other various building management control changes. The Taiwan Changgung Memorial Hospital saved 2 million kilowatt hours per year by reducing power, heat, and water consumption. And the Central European University in Budapest, Hungary, implemented microshading technology in glass structures and windows, installed natural ventilation, rainwater collectors, and implemented a smart building management system. So these are some of the examples that we could use to also implement, as well as
these examples. So we have CO2 detectors. This decreases the amount of outside air being brought into a space, which ultimately decreases the amount of energy needed to heat and cool that air. You're building traffic sensors, which coupled with building management systems allows for equipment to be optimized and ultimately controlled when it's on and off so that you're not wasting energy. Another great example is ground source heat pumps. Because the ground stores so much heat, you can use them throughout the year, and they're about 3 to 4 times more efficient than electrical heaters. Building management systems control and kind of optimize everything that is in your building, from electrical to access prevention, fire prevention, your lights and ventilation. Just these can be coupled together and then give your energy manager a really great idea of how your system is using energy, as well as places where you could save energy. Looking into the future, Siemens and other companies are looking at developing artificial intelligence that can identify, learn patterns, and then further optimize building efficiency. And then another thing that most people probably don't think about is current building life expectancy is about 50 years. By implementing smart building technology, you're ensuring that your building can stay around way into the future and can be updated frequently, and it increases your building's life expectancy by about 20 to 30 years. So where would we implement these smart building technologies on campus? A great place to implement this would be in any new building. This is just because it's a blank slate. You have a ton of freedom with what you're able to do. Places like the new classroom buildings, Mayo Hall's going to be renovated soon. Lower Residence is talking about being updated. All great places, but this doesn't mean that you can't also put this into existing buildings. You can update VFDs and pumps. However, it's a little bit more difficult because you don't want to be tearing down structures and infrastructure, because it just defeats the whole cost benefit of implementing the technology. And then the most important part is how much energy you're going to be saving, and ultimately dollars. So on average, you save about 15 to 30% of a building's total expected energy usage, depending on how much money you actually invest in a smart building technology. And then along with that, you decrease the amount of wasted energy by up to 50% over an unoptimized system, which adds up, as we'll see. So ultimately, smart building technology is very specific to the application. And we chose an example of the classroom building, which is 14,000 square feet. The smart building technology costs about $250 to $750 per square foot, depending on how expansive you want it to be. And this comes out to about $35,000 to $105,000 in cost. And again, 15 to 30% energy savings respectively.
Yeah, so like Tyler said, there's quite a vast amount of things that can be done as implementations. And so here is a depiction of the load offset using 15% reduction. And so in these calculations, we basically determined that 80% of the campus's electrical load is coming from buildings. And we determined that about half of these buildings we would end up using this implementation on, and of the other half, we'd get the 50% wasted energy reduction. And so this is kind of what the load profile would look like. 15% reduction, like I said, and in a few slides, you'll see this compared with initial load profile. And so here's also load profile using the higher value of 30%, which would be basically the most efficient that we could get. And so here's an overlay of the averages of the load profile of campus currently, and then also the 15% reduction and 30% reduction, which clearly shows that we're reducing anywhere from 50 to 150 kilowatts off our load at any given point, which is pretty substantial. And here is energy savings of the 15% reduction. We end up saving about $40,000 per year. And then with the 30% reduction, we're saving a lot closer to $100,000 per year. And keep in mind that this is not factoring in any implementation of solar or energy storage, which if combined and fully optimized, we could effectively be cutting our energy costs per year in half, which is extremely beneficial. And here's our sources, just so they're there. And a special shout out to Professor Ryan Storrs for turning us on to energy savings and tariffs and all that good stuff.
Hope you enjoyed. Thank you.